All right, now let's look at another situation, both a little bit linear and mostly exponential. Is Canada's population in the year 2000 was 30.69 million people, and in 2017 the population rose to 36.71 million people. So this time, state the number of people Canada's population increased by each year. And so since we're talking about the actual number of people, then that means we are talking about the absolute. And so we know that it's the increases from 36.71 million from 30.69 million over 17 years. And so we end up with 6.02 million in that 17-year span. And so each year, Canada was increasing by 0.35 million people per year. So that would be the absolute increase. And we could write a linear equation if we wanted to. But again, let's focus on percentages and relative and exponential equations. So calculate the percent increase each year. So in our list of formulas, we have an idea that, so we can't subtract and divide because we're talking about exponential. And so that means we're going to have some sort of exponential equation or exponential working for this. So the way we do this is we're going to take the latest value divided by the oldest, or you could say the newest, maybe that's a better term to say, is the newest value, since we've used new and old in the past. So the newest value and we're going to divide those. That gives us a decimal, which makes sense because we want something to be exponential, and a percentage is a decimal. So we're going to get a decimal here. But then we have to do something about that 17-year period. And so what we do is we raise it, so as an exponent, 1 divided by the time period. Just like we knew that to divide by 17 years, we do a similar thing here, except that we're writing it as an exponent. So let's see how this is written out in terms of the Canada problem. So we know that the newest value, the most current value, is our 36.71 million divided by the oldest value, which was the 2000 value, 30.69. And I'm going to put this all in parentheses. And I'm going to raise it to the 1 over 17 power. Notice that your exponent is smaller and always raised. Okay, so now let's go over to Desmos, or some sort of graphing calculator, and we're going to parentheses, and then I'm going to hit the division key, and when I hit the division key, it's automatically give me that fraction bar, which is a nice thing. So 36.71. 36.71. I said that, wrote something different. And our oldest value was 30.69. And I'm going to go outside that parentheses, so I'm just going to click over. I'm going to use my exponent button again. I'm going to raise it to the 1. And when I hit divide, it's going to keep it all up in as a fraction. Okay, to the 17th power, and my answer is 1.01059. Now keep in mind that the 1 represents 100%, so the 0.01059, that's actually what our percentage, or our decimal is. So 0.01059, I'm just going to write those down. So this was 1.0, I forgot, 1059. And remember, so this is 100%. That's not our percent growth, that's just the 100%. So we're now just looking at this portion. So we have 0.01059. We want to write this as a percentage, so the decimal point will go here. The 5 forces the 0 to become a 1, so we have 1.1% each year. Now we can write an exponential equation for Canada's population. So we can say P equals the initial value, and our initial value was our 2000 value, because that's the oldest one, so that's our initial one, 0.69, 30.69, times, now we need, here's our percent, so it's 1 plus, changing our percent back to a decimal, 0.011, and we're going to raise that to the y power. All right. So now let's look at a decreasing one. So we've already talked about, whoops. All right, in this decreasing situation, so oxycodone is metabolized by the body at a rate of 18% per hour. Okay, so there is our exponential. So write an exponential equation that models the metabolism. So it's the amount in our system. So A equals, the initial amount is 10. And then we have 1 minus 18% is 0.18. We're doing this every hour. So here's our exponential equation. And we want to calculate the amount that's in the system after 4 hours and after 12 hours. So again, a calculation for 10 times 1 minus 0.18 raised to the 4th power. We also have a calculation of 10 times 1 minus 0.18 raised to the 12th power. I'm going to calculate those out. 4.52 milligrams and 0.92 milligrams. All right, so we're going to use a guess and check method to figure out when 2.5 milligrams are left in the system. So when we're working with our exponential equations, the method we're going to use is a guess and check method. If you know of other methods, you're fine to use those as long as you show your work and explain what you're doing. But in reality, most of us are just going to use a guess and check method when we're out in the real world. And so we know that our answer is going to fall somewhere between 4 and 12 hours. Because we know the 2.5 is somewhere between these two numbers. So I am just going to guess 8 hours. So I'm going to calculate my 8 hours. So I'm going to find out how much is left in 8 hours. I'm just going to go to Google again, or to Desmos, and I'm going to type in 10 times 1 minus 0.18, and then we're going to raise that. In this case, we're going to raise that to the 8th power. And we get 2.04. So we're close. We're close to that 2.5 milligrams, but we got to go up a little bit. So that means we got to go back in time. So now we're going to try 7 hours. And when I try 7 hours, so I'm just going to change my 8 to a 7. And I get 2.49. .49 milligrams. Well, that's very close. Obviously, that's very close to 2.5, but let's just double check to make sure there isn't anything any closer. So we are just going to check 6 hours to make sure. We're using whole numbers here. We could get it to the nearest tenth if we wanted to, but we're really just looking for a whole number hour because you're going to take the dosage based on every hour. And so that gives us 3.04 milligrams. So we know that 7 hours is best going to approximate our 2.5 milligrams.